That's right. That's
Okay,
right.
I'm Dan Harris, and I'm going to be talking about optical sensors. Part of the reason why I wanted to talk about this, when we had the project we were doing, was it last month, where we built the ping pong ball and all that, I heard some things about different optical sensors that I thought, well, maybe we need to talk about that a little bit more. You know, like phototransistors don't work and things like that. So I wanted to just talk about the three main types, and those are light-dependent resistors, photodiodes, and phototransistors. There are other detectors, but I don't think that we're going to ever be using those. The things that are important about these, and the reason why you can go to your box of parts and pick out a phototransistor or a photodiode or an LDR and it works or doesn't work, is because of these different parameters. So we're going to be talking about wavelength, field of view, sensitivity, response time, also saturation, which it turns out we're going to demonstrate here, which I didn't get that to do that at home, but apparently we have more gain here. I don't know. And optical surface area. Okay, so wavelength. This is just a technical definition. You don't have to worry about C over F or anything like that. But we're going to be we will talk about wavelength, how it affects the response. And the visible wavelength goes from 400 nanometers or thereabouts down here where the violet is, up to about 700 nanometers where the red is. Out here is ultraviolet, out here is infrared, and most of the sources and detectors that we would be using are going to be either in the visible range or out here in the infrared. It's very unusual there are ultraviolet detectors. I don't think anybody's going to be using those. Now here's the thing. The wavelength of a particular detector one detector versus another brand of detector, the response could be way different. This detector happens to be very sensitive in the visible range and has absolutely no response out beyond about 800 nanometers. So if you tried to use this detector for the near infrared, which is out here, it's going to be a complete dud. On the other hand, this detector has no response in the visible range. You can see right up to 700 nanometers, no response. Great response here at 900 nanometers. So you might be wondering, well, why would you want to have a detector that doesn't even respond to the visible range? And
You want to answer that?
So I did a project. I got a patent on this actually years ago, because ambient light can affect them.
right.
You can put infrared if it's inside. You don't get the infrared noise, the noise light. So you can just use infrared lights to eliminate whatever you're looking at.
Right.
And they're not position dependent or dependent upon the room light.
Yes. So we're going to talk about saturation in a little while. If you wanted to make something work out here at say 900 nanometers, which is near infrared, and have it be completely blind to all the room lights and everything, this is the detector to choose. This is going to knock all that out. So
Supposedly police laser is something like 940, but I might be off a little bit.
that could very well be.
Yeah, it's about the 940 to 960.
Really? Okay. Yeah. And you can get lots of LEDs that work at 940, lots of good detectors that work at 940.
And it doesn't take a license to broadcast at that because it's light, and so you could put those big LEDs on the front of your car and wash out their light on.
Yeah.
Their light on.
Well, Mythbusters, they just bought some Radio Shack wide LEDs, and they're like, it don't work. And I'm thinking, if you had 940 but floodlight configuration,
Right.
yeah,
They sell a LED. It's about size of a quarter.
Almost.
That's not right at the middle of that fan.
Yes.
I wonder why they would do that.
Yeah, you just need something about this diameter, 1,000 watts.
Yeah, you gotta wash it out their power.
What happened to that police officer? His car burst into flames. I don't
The thing you can do is you want to put them down near the headlights and or the license plate because they'll aim for reflective surfaces. So
Okay.
but
I'm gonna,
not a hit
that
here.
could be, that, if somebody wants to create a product, that would
Yeah,
probably
they
be
have
very
them.
popular.
They're really expensive.
Oh, really?
They don't need to be. You could make them for $20. But
Yeah.
You recording this today?
Yeah.
We want is it on film now?
No, it's live. It's live. It's streaming.
Yeah.
Although I do not want to make one.
But that would be against the law.
It's for off-road use only.
There you
That
go.
would be, yes, inappropriate.
For my night vision goggles, like turn my headlights off.
All right, Dan.
Sorry.
So wavelength is very important. So you can't just grab a photodiode and say, well, that thing doesn't work. Well, it doesn't work in your application. Be careful because they're very dependent on, I mean, they're made to operate in a certain wavelength. Another thing is the field of view. These photodiodes can be made to have a very narrow field of view or a very wide field of view. And here again, the reason they do that, I mean, these photodiodes typically have a, you'll see like it's rounded here, it's lensed, and they're trying to affect that field of view for various reasons. You may not want to have, you may want to have a very narrow field of view. You may not want to detect things that are way out here. Or you might want to be able to see everything. We're gonna be talking about an application here in a few minutes where you want to have a very wide field of view. So, okay, so ping pong ball. If you had a very small field of view, that means that it basically only think of looking through some kind of tube with your eyes. I mean, that's what this thing is doing. If the light hits it here, it's not going to see. It's going to have almost no response. So again, just choosing a photodiode sort of at random or a phototransistor at random and saying, well, that thing doesn't work. You may have gotten one that had everything else going for it, but it had a narrow field of view. And like I say, there's applications where you want that narrow field of view, so you just have to make sure that you choose the right device. And then sensitivity. Sensitivity is how much current comes out of this photodetector for a given amount of light. And as you might expect, if you have a photodetector with a larger optical area, you're going to get more current out. Also, if you have a photodetector with a very narrow field of view, it's going to be more sensitive to any light that's in its field of view than if you had a wide field of view and you hit it with, say, a laser up here. Okay, so now we get into, this is really going to be about the response of the device. Now we're talking about a photodiode. A photodiode, I mean, this is a very simple circuit. This is all there is to this thing here. It's just a resistor and a photodiode. Every photodiode has some parasitic capacitance. You can't get around that. And that, in parallel with this resistor, is going to determine just how fast that photodiode or that phototransistor, well, that photodiode will respond. Now, if you look at the data sheet, it'll say like this photodiode has a 10 nanosecond response, and it, very well might. But that's if you had like a resistor that was tiny, say 50 ohms or something. 50 ohms in parallel with 10 picofarad, yeah, you could get some really high speeds. But if this resistor, the resistor I'm using on this particular demo is 1 meg. And as you'll see here in a minute, I'll be lucky if I can get it up to 20 kilohertz, 50 microsecond period. So that's the response for most of these applications, photodiode applications, is going to be determined by the resistor and the parallel combination of that resistor and the capacitance of the photodiode. Okay, so what's a phototransistor? Well, a phototransistor is a very simple thing too. It's just a photodiode with a transistor integrated all into one package. The nice thing about that is now it's still 2 leads. It's just got 2 leads. It's always slower than just this photodiode by itself, and the reason is that capacitance, that parasitic capacitance of this photodiode is now across the base collector, and there's something called Miller's capacitance, which I won't get into here, but it slows it down about slows it down by a factor of about the beta of the transistor, the beta being the current gain. But, so the bad news is it's slower by maybe a factor of beta. The good news is it's got more current by a factor of beta. So, again, it depends on your application. What are you looking for? And then light-dependent resistors. And a light-dependent resistor is nothing more than just a resistor that changes its resistance in the presence of light. They're very inexpensive, very popular for dusk-to-dawn applications. Most of these sensors that you have on a yard light or something like that are going to be LDRs. Extremely slow response. A large fraction of a second in the case. I forget if it's when it turns off or when it turns on, but one of those is close to a second for a lot of these devices. So you can't really use it for any modulated kind of application. Okay, the effects of ambient light. And I don't think I'm going to be able to demonstrate it here, unfortunately. It's an interesting thing. You think that the ambient light is just going to be a DC effect. So you turn the lights on and the response goes up. Actually, a lot of these lights, and I don't know what kind of lights we have here, but like in my workshop at home, I have LED lights. And there's a very significant 120 hertz modulation around that. You know, it's not, so it's, when you turn those lights on, it's not just that it comes up like that on a pedestal. It actually is modulated, and that will have a big effect. A lot of times I hear people say, well, it worked at home, but then I brought it here and it doesn't work. The lights are doing something funny. Well, a lot of times the something funny is the fact that you've got this extra modulation.
Fluorescent lights have that too.
Fluorescent lights,
you can actually capture it in a camera. You can see the light
yes,
dim, almost black, and then bright again.
yes.
And they also take about 5 minutes to come to full intensity
Okay.
when you turn them on. So they'll turn them on, and then they'll be at level, and then they'll, over the next 5 minutes, creep up to their full brightness.
Right.
And a lot of the newer LEDs are running at 100 kilohertz range. So that might be these. I think these might be doing that.
That's right. It's not just the 120 hertz. There's also like these compact fluorescent lights that were popular for a while. They're probably going to go away now that LEDs are becoming more popular. But you know what I mean. And then you screw them in place of the light bulb. Those, what they've done there is the ballast has been by increasing the frequency that they use to modulate or to get across the transformer, to get across the ballast. They go up to like 40 kilohertz, could be as high as 100 kilohertz. They go up to very high frequency, and so that's what allows them to shrink the magnetics down to the point where they can fit it into the socket of for a light bulb, and that can have a serious effect as well. Yes.
Hey Dan, on the LEDs, are they turning them off altogether, or is it a voltage fluctuation at that frequency?
They are, I think in most cases what they do is they actually take either the just the voltage offline, in other words, just the 120 volts AC, or they take go through a transformer and bring that down. But at any rate, they have what winds up looking like a full rectified sine wave, and so they're actually going all the way down. And
so I ripped some apart. The one thing I couldn't tell was whether they did anything to smooth the voltage. Like a good power supply, you should have very little ripple at all.
Probably not.
All it takes is a capacitor across that output to give you enough delay time to do that.
Yeah.
So it
But
wouldn't
you could
see one at all.
Well, that's
I mean, literally, you should be able to see that capacitor, and it can't be a tiny capacitor.
Yeah,
you know, like
it's probably 13
tantalum.
amps or something,
It's something like big enough for you to
Did
see
you have?
it
Did they
there
have
at
a
all.
capacitor in there?
Yeah, they had everything a power supply would have, but no big capacitors.
The cheap.
They had, they had to step down. They had some sort of rectification. There was actually a few chips in there. It's been about 6 months since I took it apart, but
Yeah, I think one of the things they're trying to do is they're trying to they use feedback to keep the current where they want it to be. They don't want it, but I don't think they'd have to average it out with a big capacitor, because your eyes will average it out. Your eyes can't see that kind of, although
About 30 hertz.
But a 50% drop in an LED, you wouldn't be able to see without some kind of machine to help you see it anyway. I mean, power-wise, from full power on an LED,
That's right. I mean, you
50%
just
drop.
you're
your
not
eye
getting-
is not going to be able to tell
No.
that.
But the
so
reason
you-
I ask is, like, our line followers, we all had some odd issues that we
Yeah.
I wondered if those lights are coming off and totally on, that maybe what it was seeing, and meanwhile we have no clue that this is happening.
Yeah, it could very well be. I mean, that could very well be the case.
Your Christmas lights that you have now, the cheap LED ones.
Yeah.
Some of those, they're just putting enough in line to break up 120 volts down to, they're just putting them in series, but they're also having reverse polarity back and forth. So they actually half are lit for whenever the AC's up, and then when it's down, the other half are lit.
Okay.
So you go driving down a street, like I can see 60 hertz in my peripheral.
Really?
I see it and it drives me crazy.
Yeah.
So if you go driving down the street with those, you'll see flickering all the way along in your peripheral.
Wow.
If your eyes are sensitive to that.
Yeah. Huh. Okay.
Of course, it also means if you're playing with LEDs, you need LEDs that can take that kind of back current for like the full.
Yeah, reverse voltage.
Mm-hmm.
Yep.
Okay, so this is just a chart to show the differences. So the photodiode is very fast. Its sensitivity is low. Its current out for a given amount of light hitting it is low. So that's the trade-off. The phototransistor is going to be, it's going to be slower, but it's going to have a lot more gain. And then the LDR is very slow, very inexpensive, and it has a very wide field of view, because there's usually no, that I've seen anyway, there's usually no lens on it. Because if you think about like a dusk to dawn thing application, you don't really, there's no reason that I can think of to put a lens on there. You just want to see is it light or not. So then the last thing, these are going to be eye charts. I'm sorry, but what I did was copied a couple of sheets from the data sheet for this photodiode, just to show you what you want to be looking for when you go through these things. So this is an SFH203P from Osram, and so this was the main reason for choosing this. This is for the ping pong ball application. It's got a very wide field of view, plus or minus 75 degrees, so it can see almost the entire ping pong ball. Capacitance is 11 picofarad, and in fact that will be even less because of the fact that we've got enough reverse bias. I'll show you the curve in just a second here. So here's the curve for the capacitance, and you can see that, you can't read it, I'm sorry, but you get up to about Well, if you get up to about 5 volts, you're down, instead of having 11 picofarads, you're down to about 4. And if you take the voltage all the way to like 20 volts, you'll have 2 picofarads. So if you're really trying to get high speed out of this, you'd want to be thinking about what reverse bias to use for it. And then the last chart here shows the how the sensitivity changes with the angle that you're coming in at. It's not, you know, we say that it's like 70 plus minus 75 degrees. Of course, it's like a flash. If you think of like what a flashlight does, it's not as if you have constant intensity inside the circle and then everything outside the circle is no intensity. It gradually falls off. And the same thing is true for a detector, for a photodiode in this case. You've got maximum intensity at 0 degrees when the light's coming right on, and by the time you get here to 75 degrees, it's down to about half the power, half the sensitivity. So that's it as far as the presentation.
What's the difference between a photodiode and a pen photodiode?
None. Oh boy, I got to go back about 50 years now to my semiconductor class, but the PIN stands for P, positive, intrinsic, negative.
Oh.
And you can have PN, and I've told you just about everything I know now, so I don't want to go any
So
further.
it's PIN, it's not.
Huh?
It's not pen, it's PIN.
It's PIN.
Okay.
Yeah, it's just an acronym.
Okay.
It's like a PNP transistor and an
Yes.
NPN transistor. So
Right.
It's just basically internally wired backwards from the way to normal for that circuit.
What's that?
You did the part in the
So is
Here?
that like,
Yep.
like normally open, normally close,
There you go.
when you activate the
Okay.
light?
So,
It's like
It's-
when
if
do
you're done with that,
transistor,
we'll turn off the
you're already
TV.
putting power into the base or
Here it is.
Right,
sending
so-
power
Oh.
out.
TV
Yes.
power?
Right, so it would be,
So it's the same
one of
thing.
them would be when it's dark,
Yeah.
current flows.
Yes.
No,
And one of
is it
them,
good?
the other one would be when it's dark, current doesn't flow.
okay, so
Yeah, okay.
we've got a function generator here. It's set at 1 kilohertz, and if things are still working, you'll see. Oh, I wanted to leave this on. I should have. Because I've got the oscilloscope here, but I really wanted to show it up here because I want to be watching the oscilloscope to see if I'm doing this right. Okay, so
Push the button again.
It's ready to go.
okay,
Should be.
I don't have to like.
No, you shouldn't.
Okay. Do I need to select quick share for Windows?
You're running.
Oh, that's right. Okay, so let me just bring up the. Let's see. There we go. So let's turn this on.
Just right on the sensor.
Okay. This is not much of a micro positioner. I think it might be older than me. The wing nuts have broken off and all kinds of
It's
stuff.
not made out of dirt, so I doubt it.
Yeah, yeah. Okay, so, so this is 1 kilohertz. And you do see a little bit of, see this where it's separated a little bit here? That's probably 120 hertz. If we,
That's the signal off your
Can you
function
explain-
generator?
yes, okay.
explain this.
I'm sorry. The yellow trace is my laser drive. So it's going 0 to 5 volts. This is the laser that was in the kit that we got last month. And so he's turning on and off at a 1 kilohertz rate. He's turning on, he should be turning on here for 500 microseconds and then turning off for 500 microseconds. The blue trace is, remember that photodiode with a resistor? Well, the blue probe is across that resistor, so it's looking at the voltage across that resistor.
The RC circuit, because it's dying
Yes.
off slow.
Right. And so weirdly, and I have no explanation for it, other than this is how demos usually go, but I had less gain at home and faster response. So we'll see what the response is going to be this time. And what I wanted to do was to
What's the voltage? I can't read that. The blue, what's
the blue is 1 volt per division. So
Okay.
this is approximately 2 volts here.
What's the
Which is
most
a little-
it will go to, like if you hold it for a length of time, like without a square wave, just hold it?
It should be here. Although, what's weird is now 2 volts. I have what is my? I've got 3.4 volts. Is that what it said? Yeah, 3.4 volts. This should be going higher. So I'm not sure what is.
It's just not getting strong enough signal from the laser?
I don't know.
Well,
No,
you
it's
get
getting a
a
pretty
point-
strong signal.
Do you get a 0.7 drop best case scenario, like when the,
No, it doesn't work like a.
okay,
Keep in mind, this is a reverse biased photodiode, so it's not gonna work like that.
okay.
I don't know. It's
But it's high enough to trigger though.
oh yeah,
Because what you're doing really with the diode is you're reverse biasing it, and then when the signal hits, you're dropping the gate.
On reverse bias.
Right, so you're letting it become not a diode anymore when the light hits. Right? So it
Piece of
doesn't,
wire in a perfect world, is that, it should be a short,
it would be a short, yeah. Yeah, but when the light comes on, so the gate, the current comes out, hits the gate, but the light hits and it dumps.
okay.
And then when it's, turn the light off, it closes the gate.
The
again.
light is your base, essentially, your.
Yeah.
like
The
I
sig-
said,
right,
it's
light
FET,
is the
it would be-
signal.
yeah.
Yeah.
But there's some resistance.
okay. So here's you can see
You're picking up that bias.
you can see very faint modulation on the bottom here. You see that?
He's got to get rid of that.
That's what I'm saying.
That's the 120 hertz.
Yeah.
So that's coming from ambient light?
Yes. Yeah, if we could get
Well,
the
they were
lights off
right? You
completely.
can see
I don't know
how yellow was here, but the blue was down, so it was down on
He's
both
got
of them,
the
so it just
blue
had
one.
zeroed. If you raised all of it up where the zeros were the same, they would.
Is that live or is that?
I think
just a
this one's-
capture screen?
What?
Is this
This,
live or
it's
captured?
capturing the, it's not real time. I mean, it's not,
But right now it's static though, it's not refreshing.
no, it's not refreshing. I wish it was.
Did you just change the scale, is that what happened here, or what?
I changed the scale on the time.
Okay.
So, I wanted, because I wanted to see if we could see the 120 hertz. It's very, very faint. At home, it's much stronger.
So where is this 120 hertz? Is that on the bottom, on the yellow?
Yeah.
the blue?
Yeah. And now you can't see any, before you could see, there was like a little ambiguity about where the trace was going at the bottom here. I'll turn these lights back on, you can see what I'm talking about.
So it's showing you multiple, when you had that trace, it's because it's showing you multiple of the way you
Yes,
have it right now.
right.
Okay.
What's your time period in this one?
Right
500?
now, I've got it set for
So you're only at-
200 microseconds per
Yeah.
division.
Right, so your whole screen is, I'm thinking your 60 hertz, if you're picking up a lower frequency wave, it might not be detectable at that time. When you zoomed out, you could see it, right?
Well, let's try a lower frequency. Let's see what happens. So I'll take it down to, let's say, 100 hertz.
Yeah. If you put it at 60, you might get a harmonic. Which would amplify. Right. Which would amplify or.
If what now?
If you put it at 60 hertz.
If it's
Yes.
240,
Oh, you want to
would get it every other.
Right.
Let's
you
try
do
it at
every
100.
other.
Yeah, let's try it at 60.
Yeah.
60 hertz.
On that one, you should see it twice per
Yeah.
cycle.
Yeah.
Okay, why?
The laser's a little off.
So say maybe at 10 kilohertz
Yeah.
or whatever it was at, 100 kilohertz, it was so, you're
Yeah.
down so much that
Yeah.
the lower frequency is not visible, it's almost
Right.
flat.
Yeah. I totally get what you're thinking.
Okay, I'm changing the frequency.
There's a hole for the touchdown.
Frequency.
Or even 65 hertz. you can see all this.
Uh-huh.
You see it drift across.
All right, here we go. So 60 hertz. Now I've changed the time scale so that
Look at that.
this is now 4 milliseconds. And probably, I'm just guessing, that this
That
little
ripple.
thing down here, the ripple,
Yeah.
is probably the additional modulation. There's a phase difference between this 60 hertz and this 60 hertz or something,
Yeah,
right?
but it's
Yeah, that's true. We're not like synced in.
No, we're not.
No, right, yeah,
We're
but
not
it
part
would
of
be
it.
consistent.
Yeah.
Right.
So you're only seeing it on the bottom, why aren't you seeing it on the top?
It's saturating, and I don't know why, because it didn't do that at home. But it's saturating here, and see, the thing is, it shouldn't be, because it's only going up to about 2 point something
Well, all I'm
volts.
saying is, if you're cycling something at 60 hertz and you're only seeing it on the bottom, I'm suspicious of that, because I would also think you would see it on the top.
You should, but if it's saturating up here,
You're not.
then it can't go any
Yeah,
higher.
You don't have direct light though either.
Yeah, you're
This
not
is
getting
all-
saturation
if
from
you
the
put it-
above lights. You're
if
getting
you put it
some
right
signal.
underneath the light, it might be more of an issue.
So cover it up completely and see if we now
Well, what
do
I'm
the
wondering
testing
is-
and then.
Is in fact, since we're looking at the bottom, is that a ground effect? You know, where it's trying to drive it to ground?
I don't know. I mean, what would be cool is if it would work just the way it did at home. But, it's, and
That's what
I
Edison said.
try to do real-time troubleshooting, but that doesn't usually work very well for me, so. Let's see what happens, and this is gonna be, at
So
home I was able to get it up to 20 kilohertz, and it still was hanging in there.
So why, I talked to Sam about doing some of this stuff.
Yeah,
He was, and what I was doing with the photodiodes is trying to amplify the signal.
yeah, you can do that,
But which is better, the biasing is a lot simpler.
sure.
Because I mean, the sensors I'm looking at, they're only getting you like a couple hundred millivolts with really strong light on it.
Yeah.
I don't know what this one does, but
Well, this is the laser that came with the kit.
yeah.
And this is that SFH 203P photodiode, which is a 20-cent photodiode that has the wide field of view. So, and a 1 meg ohm resistor. And in fact, we're getting too much gain out of that 1 meg. We'd be better off with 100K. So we're getting plenty of response here.
Well, like the couple hundred millivolts I referred to, I just put my scope right on the sensor, not plug anything else, and just do light on it, and I was getting that out of it.
Oh,
But-
right on the sensor with no resistor?
Yeah.
Okay,
But-
that would really be slow. Because you don't have it, you need that resistor.
Right, yeah, I understand the function of the resistor, but I was thinking going that through like an op amp or something. and trying
Oh,
to
you
boost it.
can.
But
You
I know
can.
which for what we're trying to do here.
Yeah.
This is a much simpler.
Oh, yeah, you don't,
circuit. So-
that kind of thing is, like, if we wanted to get, like, let's say we wanted to run at 10 megabit per second in outer space with satellites, hundreds of miles apart from one another. we would be doing all kinds of fancy stuff with amplifiers.
Because what you're doing with that amplifier is you're making that photodiode into a phototransistor. You're just doing it externally.
That's right. The transistor of the phototransistor is an amplifier.
Mhm.
That's one of the advantages of. And the reason I didn't use a phototransistor here was that I don't need that extra gain. That's already too much. Plus, what I found was that this had the widest field of view of any device. Between all the photodiodes and all the phototransistors that are in DigiKey cells, this was the widest. So I said, okay, fine. Wasn't anything more complicated than that.
So, yeah, I'm a little lost. Can you talk about, like, you seem to be indicating that you weren't seeing what you expected to see. Can you talk about what you expected to see and why it matters, or what you're looking for?
Well, why it matters. Because I thought we were talking before about how you wanted to be able to use different frequencies so that, like, if this guy hit it with his laser, you'd know it was him.
Yeah.
And then if this other guy had a laser over here, you'd know that it was that guy. So they could each have their own frequency, but that's only going to work if they can actually be modulated at a decent frequency. When it was working before, when it was working the way it was at home, I was getting a smaller response, actually like a couple hundred millivolts, but faster. So now it's like it's got this extra gain. I'm guessing maybe I have had a bad connection because this is a pretty kludgy setup. I have to.
What does that mean when you say?
What?
When you say it's getting an extra gain, what does that mean?
Well, I mean,
for dumb people?
No, I mean me. It has more gain, meaning that it's acting like it has a bigger resistor here than it had at home. Or maybe the laser's gotten more powerful. I don't think so, because you can I can tell from just looking at it that it's about it seems to have about as much power as it had before.
So you're
distance you're using too?
We have some of those resistors in those kits.
You're also saying
Would that help?
No, I don't want to start, because we'll get into, like, you'll all be watching me
So is
trying
this
to-
signal not readable? Like, if I hook
yeah.
this up to an Arduino,
Oh.
is it not going to figure out the frequency?
Oh,
or-
can you definitely figure out the frequency?
well,
Because
it's the square shape, right?
this is, and this is 2 volts. So you've got an A to D converter on your Arduino, and it's plenty fast to pick up this is 60 hertz. Let's
So
go
then
back
what
to.
was the problem on the other one? Was it not clean enough for a signal, or how do you?
The other one.
The previous signal that you showed the first time, was that not clean enough?
Well, I was
It's,
trying
no, they were both clean enough.
Okay.
My concern here is just it's not behaving the way it did at home.
But it's functional? Like,
It's
it would
functional
still be
here.
functional?
It's functional at home. I'm just it just bothers me that they're not the same.
Okay.
When you referred to gain, you were more meaning that at the same frequency, instead of having the blue being a square wave, it was more rounded.
Well, that's the when I talk about gain, I'm talking really about the resistance, because you've got a current out of this photodetector, so it's just getting multiplied by the resistor. That's the gain. Bigger resistor will be a bigger response. That's all I was really getting at there. But then you have the resistor in parallel with the capacitance, and that I wasn't seeing at home when I was running it at 1 kilohertz. I'm going to put it back on 1 kilohertz now to, let's see here.
Why are you running this at 3.5 volts?
You can run it at, we can run it at whatever. We can, it would be interesting actually. Let's see what happens when we run it at, say,
The laser was 5.
let's run it at 5. See if that makes any difference. So, ooh,
Sounds exciting.
Sounds
what?
Said it sounds exciting.
It-
You went whoop, something happened.
The response definitely went up. Let's try some more. I can.
We can't
Is
see it from
this
here.
is the laser power you're cranking up?
It is the reverse voltage, the bias voltage on the photodiode.
And they say
Yes.
the diodes, the capacitance becomes bigger with more
Ah.
voltage.
This is looking
That's how
more like
radios,
it.
digital radios work.
I like this.
Yeah, well,
Can we
can
see?
Yeah.
Yeah, I'm going to show you. I'm sorry.
I heard it's exciting.
Yeah.
Good story.
So, I mean, it doesn't look that much better, but now you're asking about like the top part. What was happening was it was going high, but it saturated, couldn't go any higher. Now that we've turned the bias voltage up, it can go, actually, now we're in the region where you want to be careful because this is now 6 volts is exceeding, you know, if you wouldn't want to bias it more than whatever your Arduino is capable. You wouldn't want a 6-volt signal coming into your Arduino, but you could bias it for 5 volts like we had before. So let's try it.
But if you needed it for sensitivity, you could run that at your higher power, and then you could use a divider circuit.
You could do
send it
that.
into the Arduino.
How do you
Certainly.
tell which
That way you'd have the
laser-
sensitivity and voltage.
Half a volt from
There's only one way.
whatever you're operating at.
Yeah, I know, but if there was a second laser, what are you looking
Oh,
for?
the frequency.
The frequency would be different between lasers?
Yes.
Based on how far away it is?
Yes,
or-
and that is not.
Well, we were talking
Not
about
how
in
far
the
it
game we
is.
would modulate the
Okay.
gun, the firing laser to be a different frequency on each robot would
Oh,
have a
okay.
different frequency.
Okay.
And so
Alright, then that makes sense.
Okay, we're back at 1 kilohertz, and you can see it's starting to. The RC time constant is such that it's now just about starting to. You're losing some amplitude. Okay, so 1 kilohertz for this configuration might be about all she wrote. However, if you used a smaller resistor, say 100K instead of 1 meg, you'd have smaller amplitude, but he'd be hanging in there. He'd be looking good.
Here's a quick question. The 1 kilohertz is produced by the red laser, right? So we're illuminating the ping pong ball. I wonder how long the ping pong ball glows after the light's removed.
Well, that's an interesting question, and I don't think we can get it dark enough in here, but like in my workshop at home, if I turn off all the lights, this ping pong ball has a nice red glow. And I think the reason for that, I was trying to figure out, is that fluorescing? I don't think so. I think what happens is the light hits it, it's coming out on the other side, inside,
A little reflection maybe.
and then it spreads out everywhere and gives you a nice constant,
Yeah.
glow. Yeah, it's pretty cool looking when the lights are completely off.
You're talking about as soon as you stop firing?
Right. So if it wouldn't glow anymore for reflection, I was thinking fluorescence, like you're saying.
Yeah.
But now reflection, like if it had to do.
That's what it is,
Getting
I'm pretty
false
sure.
signals or?
Yeah.
Yeah, I was asking that question before.
I wonder if it bounces 5 times that are useful.
It's negligible.
So
Yeah, I
what
would-
so we're firing at 1,000 hertz.
Right now we're at 1,000
We're
hertz.
firing at 1,000 hertz.
That's
Do we
right.
know, do we know what the actual frequency of the laser is?
The laser is probably, just based on the color, at about 650 nanometers.
So that's at the upper level of the human eye.
That's right. It's
Okay.
the red.
So, and we're still seeing red, so we can't see above 700 anyway.
Right.
We can't.
Right.
But can the photodiode see above that?
This particular one definitely can.
Right, so-
He's
so-
got a peak response at 850.
850. So is I guess what I'm asking is what is the bottom number?
The bottom number.
So you showed the
wavelength,
peak.
you mean?
Yeah, you showed
As
the
far as
peak.
wavelength?
You showed the peak. You know, it was 900 was the center of the one. So what is? And you were saying that it's got a cutoff lower, so it's can only see stuff above 700.
Well, you did. I don't know. Yeah, if you notice that curve for this particular photodiode, the SFH203P, it has a peak at 850, and then it gradually goes
Yeah, but
down.
I want to know what the lower number is.
And at red, it's about 75% sensitivity. So if you got down to green, it'd be probably 50%. I mean, we could go back to the chart, but it's on that order. It would even have a small response at blue. If you hit it with a blue laser, it would have maybe 10% or something. Is that?
No, I kind of lost me.
Yeah, I just wonder what
They
the
kind of go
cutoff
back
is.
to the reflective or fluorescent,
Yes.
okay?
Yes.
Because, like I said, I work on laboratory equipment, and we work on fluorescence,
Sure.
okay? So we're hitting it with a laser at a certain wavelength,
Yes.
and then we're looking at everything above that. We don't want to be looking at that laser beam. We don't want that.
All right.
We want to be looking at the fluorescent, this is our equipment. We want to
Yes.
look at the fluorescence, because what we're doing is we're striking, a sample with a laser, and we want to see how it fluoresces above it.
Right.
Does that make sense, or can you relate that to what we're trying to do, or?
Above the frequency you're hitting it?
Yes, yes.
Okay.
Blind
Yeah.
medium?
Oh, what you're saying is, okay.
Or maybe
I think what he's saying is that's hitting it at whatever, 680 or whatever the frequency of the LED is,
Uh-huh.
hitting that.
Uh-huh.
But the ping pong ball might change the color of it to a different frequency.
Oh, if it was fluorescent.
But that wouldn't
Or
change.
just, even if it isn't, right, it's not the same intensity of red, right, it's a little more muted, kind of, right
Well,
now.
I'm just saying is we're at the limit of what the human eye can see here with these LEDs.
Yeah.
So what I'm wondering is if you put a different sensor in there with a higher frequency response,
Yeah.
would it also see it?
But that's the
Now, would
purpose
that-
of using a laser LED there, is because you get a nice relatively clean frequency out of
Yeah.
it. So if you then turned around and put a different sensitivity range across there of your sensor, all you're gonna do is cut yourself down. If he chose the right one here, that's, somewhere in the range of the 960 or 940.
Right, but what I'm saying is if you're hitting that ping pong ball with a
But it wouldn't
liquid-
change the angle, because the angle is an optical thing and not a,
I'm not talking about
Oh.
the angle.
okay.
What I'm saying is if you're hitting if you're hitting the ping pong ball with a laser,
Yeah.
and it fluoresces, that
Oh.
base wavelength is not going to make it into the
Right.
Yeah, this is not
He needs a
fluorescent. here.
ping pong ball reflective frequency
But the ping pong
perfected.
ball, but the ping pong ball might not transmit. I think what you're saying is like, well, I'll explain.
He's saying a ping pong ball
White
surface
light,
is gonna
white light
change the
hits
frequency.
this tape, or hits this top of this red, right?
Right.
White light hits it, but only reflects red,
I don't see.
right? The
Yeah.
ping
It's
pong
absorbing
ball, the
much
red
color.
hits it, but maybe it doesn't reflect red really well.
Because it's not a perfect white, so it's
It's not,
gonna lose
it might
something.
absorb some of that red wavelength and only pass,
hit it with, put it
a little above or below, but
See,
the range of that
But
LED
he's got a
isn't gonna
range
be
of
that
that.
different.
all right, here's
It's not
one
like
thing.
it's gonna shift it from red to blue.
If I hit this white page here with a laser, now the laser has a very direct path, but once it hits that paper, it goes out in all directions
Right.
as it's reflected, which is why you can see it from where you are and you can see it over here and so on. I think the same thing's happening with this ping pong ball. The red light some of it's transmitted through, and then from there it's emitted.
Right.
But as it's dispersed, it literally does change frequency,
Right.
just not significantly, but
Oh.
it has to.
It has to.
Oh.
But-
It
but-
bends, that's what makes it bend.
Okay, well,
But is
But
there a
would
red
it-
dot on the back side of that
No.
ping pong ball?
no,
So everything when it hits, everything is
So-
being diffracted somehow.
everything's going,
So-
yes.
So I assume that this ping pong ball is a normal ping pong ball.
No.
Actually, no, it's a
It's a laser
it's a
ping
crappy
pong.
ping pong ball.
Yes.
As soon as I start handling it, you
It's
see this,
technically a beer
this dent
pong
over
ball.
here.
Yeah, they're horrible. You can't play ping pong with them.
Oh no,
They're like
I dented it right away and I couldn't get it
But
out of there.
But they're good for refracting or diffusing.
Yeah, it's a
whatever.
good- it's a
The
good-
reason I'm asking, because I was in the grocery store last week, I actually seen glow-in-the-dark ping pong balls.
Oh, okay.
Ping pong.
I don't know what that,
That's for your drunk people.
That would mess you up too, because if you shot energy into it,
Yeah, then you're gonna
and
get-
it started to fluoresce,
yeah, it'll start to
then
fluoresce.
it would like change the frequency that you would be
Well,
getting from the
Yeah,
output,
but
because
what I'm saying is if we were to use something like that for our game that we're gonna play, it would be a little bit more dramatic, because then we'd see the light,
The residual hit.
the hit from the.
That's true.
glow in the
It'd be-
dark
it-
bulb.
Well,
efficiency wise, so I think it'd be better to light it up internally, like
Yeah.
when you take a hit, you light it up
Well,
with a
that's what I'm
yellow
saying,
light
they-
inside.
Glow in the dark.
And that way,
Well, these, you turn the lights out, just the red on there, it already gets some,
Mhm.
that you can recognize it, but yeah, then if we backed it up with, you know, a quick LED flash, you know that, okay, it got hit. So-
Yeah.
Dan, can I ask you, so what did you do exactly that was different from our project? to
Well,
improve?
I believe you're using an LDR for the project. And which is fine, but that can detect when it's hit with light. You can't modulate it like this and get any kind of response.
It won't turn on and off fast enough
Won't
where
turn
you
off.
actually have
Yeah.
different frequencies.
And what did you use?
I used-
just a photo.
I used a photodiode, that SFH 203P, and I'll give you the charts if
So
you
it's
want.
just a matter of swapping out the sensor?
Yeah.
And that really makes
Right.
all the difference?
Oh, yeah, that'll make all the difference. But the thing is, it's not just any old photodiode. It has to be a photodiode that has the right field of view, big field of view. Most of them are much narrower. This one's very large and has the right wavelength, can handle red, you know. Because a lot of them, probably half the photodiodes you buy, if you weren't, thinking about it, half the photodiodes let's put it this way, half the photodiodes that are sold are probably have no response at all at red or any visible wavelength. And that's intentional. They want it that way because people have applications where they want to hit it with an infrared laser and not have the ambient light messing with anything.
Did you see that?
Oh, very good. Oh, I like that. Yeah.
What's it doing?
It's just taking the infrared off of this
And it's
guy.
too bad
What would the signal do?
It was pretty strong, wasn't
See
it?
it?
it was very strong. Yeah.
Can you do a screen capture?
I don't think I can get it to. Oh, I know how I can do it. I know how I can do it.
So you're passing it through the bulb.
Do that again.
So
Oh, you know what I
you're
have
looking-
to-
You're looking at. the-
Let me set it up for single, and I'm going to have to set it up to. I don't usually use this. Okay.
You're trying
Channel
to-
source.
Well,
Well, what I'm saying is, I'm seeing the laser bleed through your fingers, so.
Oh, I haven't been working out enough. I'm not opaque.
What's going to happen? Do it now.
Oh, yeah, that's
It didn't. Why didn't that?
So
Oh,
now-
I can see what's wrong.
So we're not saying
Okay.
the bulb fluoresce, the ping pong bulb.
There we go.
It's-
Okay.
You're not seeing
Okay.
it because it's infrared.
Right.
Okay.
it's fluorescing, just not where.
Now
signal
let
is.
me
So you can look at
capture
the camera,
this.
You might see it.
Right.
Okay, this is the
Come-
code.
Probably
It's
would
off
see
the
it in your
screen. I
The
should have.
camera's in your phone, can pick that up.
Okay.
So this
Really
is
strong.
this is the code that the remote was putting out. So now the thing, here's something though about that. You gonna do that again?
He's trying to see if you can see it with the,
Nah, it's too weak.
Okay.
I can probably see it coming
yeah,
out.
there you should see it.
Whoops.
Okay, do that
I
again.
think see it's purple.
Oh, that
Those
was
cameras probably have IR filters on them.
okay. There we go. There we go. So
Shoot it right into the camera and see if you see it.
Yeah,
You-
it
you
is.
do.
It
You
is
normally
purple.
see a white light.
so there's
That's how you
the
check
code
see
that
the
was being
remote
put
works.
out
Is it?
Yeah.
from your remote. Now, but here's the thing. This laser is putting out a very narrow beam, and if we put it, say, across the room, it would probably be as bright, almost, as what it is at this distance. But
you could
but-
use something like this as a, it's the grenade effect or something.
Yeah, I was just thinking that.
You put that on the backside so we can actually see how beam.
I've accidentally pointed it towards me, and
well,
they
this is
still work
probably infrared,
sometimes.
I imagine.
It's
Because
right,
they're-
I mean, with
Yeah,
Flagging
because
off
it's-
something,
they're
I'm
the
sure
same
this
frequency, it's
laser.
just the laser is focused directionally, that's the difference between an LED laser and other lasers.
Oh,
This guy?
how big that dot is?
This guy is?
That guy.
He's
It's
as
here.
big,
It's
well,
a
can you
few
see it over?
millimeters probably.
Unfortunately,
I see the light.
no, if you come over here, yeah.
It's
3/16.
2 by 3, 2 millimeter by 3 millimeter.
Yeah, it's about a 2 millimeter.
Those are pretty tight.
It's rectangular. It
But-
will spread.
But it'll spread a little bit, but I
It's
mean,
got a
it's
little
gonna
bit of
be,
artifact to it.
whereas this guy is an LED, and he spreads out And you can tell that when you're at home, when you turn on your TV, you don't have to be directing it right at the TV. You can have it over here and it'll still do a pretty good job of turning that TV on.
And that one's actually a really strong signal.
But the problem with that then is that the farther you get away, the more it's going to go down, because it's putting out that light into this solid cone, the solid angle, and so the more you spread out, it's increasing this way, it's increasing this way.
So this game that we're going to eventually try to play, we're going to have 10 combatants in the ring, right?
I don't know how they're planning on doing it, really.
Well, I'm
Gotta
just
ask
saying,
Jason or
there's like
Josh.
10 people here. So if we got 10 people in a ring,
Yeah.
for lack of a better word, it's fight to the death, winner takes all, right?
Uh-huh.
You
Yeah.
know, so, you know,
Pink slips. Somebody's walking away with 10 robots.
yeah, so you would not want to know who killed who.
Right.
Because they say, oh, I'm dead, you know, and they said, well, I'm dead, you know. Or-
Zach's gonna hook his to his prize fighting battle bot. Coincidentally, you might get hit by the laser.
Or anybody just picked up a
Yeah.
Well, I'm just curious, if any thought has been given to that.
Get that caught in there and it
Yeah.
gets squished.
Okay, all right.
You mean as in, you know, who hit who and all that?
Yeah,
That's what the modulation is for.
right, that's what I'm
So
saying.
one person's at 1K, somebody's at 2K, 3K, 40, whatever,
Right.
whatever it needs to be.
Right.
Like the Kruger system that I came up with was using a
Is that the,
transistor.
presentation?
It was,
I think
I
we're
could
done.
do between like 4 and
Yes.
20.